Good afternoon, everybody, and welcome. I'm very pleased to have Professor Tatiana Rappoport with us today. So Tatiana comes originally from Brazil, where she did her PhD with the Museo Continentino that maybe you know from his book on patterns. She worked on disordered quantum spin trains for her PhD, then went to a postdoc to Notre Dame in the US, where she worked on dilute magnetic semiconductors. Came back, became a professor at the Federal University in Rio de Janeiro, where she worked on many different topics, from quantum Hall topological insulators, spintronics, and optical properties of 2D materials, disordered systems, etc. She was awarded the L'Oreal Prize for Young Researchers, the Newton Advanced Fellowship of the Royal Society in London, and currently she is a professor in Portugal at the University of Minho, where she works on orbitronics and photonics. Besides all the research, she is very active in outreach, and she has been stimulating a lot poor girls from the favelas in Brazil, doing a marvelous project that was awarded with the Nature Prize for outreach. Girls in the circuit. Tatiana.
Well, thank you very much for the nice introduction. First, I would like to thank Cristiane for the invitation for this talk. It's a pleasure to be here talking to the quantum materials community. Well, I checked the previous talks on this series and I talked to Cristiane. So I decided that because Orbitronics is quite a new field, I will give you a very general overview of the subject. And then, so I start talking a bit about spintronics. Then I will move to a very general introduction of orbitronics and discuss why I would like to study orbitronics in materials. Then I will talk a bit about different orbitronic phenomena and experimental results. And finally, I will move to my research field, which is actually orbitronics in 2D quantum materials. So spintronics has been an important player in the information technology industry by using both the spin-up and the charge of the carriers to encode information. And the main goals of spintronics are to electrically control the magnetic properties of materials or the spins, or conversely, magnetic control the electronic properties. But the thing is that spins normally don't couple with electric fields. So in order to induce this type of coupling, we have to use some specific key ingredients. One is magnetism. And we can, in a very simplified picture, think about the exchange interaction between the localized magnetic moments in a magnetic metal and the spins of the carriers, and they produce a relative shift of the band structure of spin up and spin down states, and generating, spin polarization at the Fermi energy. And this is at the heart of several phenomena, like, for example, the giant magnetoresistance, magneto-tunneling, or like spin transfer torques. Another ingredient that can be used is the spin-orbit coupling. Why the spin-orbit coupling? Because in solids, the spin-orbit coupling actually couples the spin of the carriers with the momentum of the electrons. And in this way, it's possible to use the spin-orbit coupling to actually make the electric fields interact with the spins. So this is what we do with spin-orbit coupling in spintronics. And in the last maybe 15 years, we've been gaining a lot of understanding about this type of interaction and how we can use it to manipulate spins in solids in several spintronic effects. One example of this type of manipulation is the spin Hall effect. So in the spin Hall effect, we have a charge current entering a material with spin-orbit coupling, and it produces a transverse spin current, and it can give rise to spin accumulation at the edges of a material. And this effect can happen with what we know as the intrinsic spin Hall effect, where actually the crystal structure of the material and the spin-orbit coupling makes spin up and spin down states respond differently to an electric field, and then we have this effect. Or we can have the extrinsic spin Hall effect, where actually states of spin up and spin down states, they scatter differently in the presence of impurities and spin-orbit. So also in the line of this electric induced effects, we also have the Rashba-Eldenstein. In that case, in materials where you have a broken inversion symmetry, due, for example, because of an interface, if I apply an electric field, we have a current passing the system. There is an imbalance between spin up and spin down states at the non-equilibrium Fermi surface that gives rise to a magnetization at the surface, which is perpendicular to the charge current. This is the Rashba-Eldenstein effect. So after this little overview about some spintronic effects, including spin-orbit coupling, let's move to orbitronics. And we can bluntly say here, for now, that orbitronics is basically the same as spintronics, but instead of operating with the spin of the carriers, we want to operate with the orbital angular momentum of the electrons. And this name was coined in a work of Bernevik, Hildren Zank in 2005, just a few months before the PhD model, and that paper came to life. And there was no much activity on this for almost 15 years. And maybe in the last 6 years, more or less, there was at the beginning a very timid increase of activity in this field, first with some theoretical proposals, and finally, in the last 2 years, we're beginning to see consistent experiments on orbitronics that I will cover in a bit. But first, let's think about the orbital momentum in free electrons. So, first, here. Yeah.
Every time they join, you get a beep.
So, we know that if we have a plane wave, free electrons, we have a plane wave, they don't carry orbital angular momentum. But a paper from Franco-Nori and collaborators from 2007 showed that it's actually possible to imprint orbital angular momentum to free electrons. Instead of producing just Gaussian wave packets, we use Hermite Gaussian wave packets. And semi-classically, we can see that the front end of these wave packets, they have an helical type of motion in this direction. And these wave packets, they interact with both electric and magnetic fields. This is an illustration from that paper. You have the wave packet moving, and with an electric field, and we see that there is a deflection of the wave packet depending on the orbital angular momentum. And in 2010, several experiments show that by different techniques, as for example, using nanoscale diffracting patterns, it is possible to imprint this orbital angular momentum to free electrons in free space. Now, if we think about a solid, we can think about the lattice structure of the solid and the orbitals as working as the diffracting pattern I was showing the previous slide. So they can actually imprint orbital angular momentum to moving electrons in a solid. And I want to highlight that this orbital angular momentum can come purely from geometrical aspects. So even if the electrons that are moving in the solid originate from s orbitals that don't have any orbital angular momentum, or they can be the interplay between the lattice geometry and the orbitals that constitute the material. And in most cases, is the second scenario. Okay, so the idea is that we can manipulate orbital angular momentum almost like we manipulate spins. And I will show that there are several experimental results doing these manipulations in light metals. Now the question is, why would you like to do something like that, right? And the answer for this comes from the idea I was discussing before, that in the case of spintronics, if you don't use magnetic materials, the only way to make the electric field interact with the spin is through the spin orbital. But in this case, orbital angular momentum can be manipulated directly with an electric field. So you can bypass the need to use spin orbit coupling, and this has some practical implications, because then you don't need heavy elements that are very scarce and difficult to extract. And this can be seen in this plot of the abundance of atoms as a function of the atomic number and in log scale. And here in blue, it's a set of metals that you normally use to generate spin currents through the spin orbit coupling in spintronic devices. And in orange, the set of metals that we discussed that can be used to generate orbital currents. And you see it's orders of magnitude difference in abundance, which means that using orbital currents instead of spin currents can open new avenues in spintronics in the direction of being cheaper and cleaner technology, because this distraction, of course, is environmentally damaging. Okay, so like in spintronics, and at the beginning of spintronics, we will always see this kind of slide. We have non-equilibrium phenomena when you need to inject and detect orbital angular momentum. We need to manipulate and we need to analyze, for example, what happens with this orbital current inside the material. So it's orbital relaxation. And in fact, we should expect very non-equilibrium phenomena that are very similar to the ones we see with spins. Like, for example, the orbital Hall effect I was discussing, or the orbital Rasch-Beilstein effect, orbital torque, orbital pumping. And I will start with the orbital Hall effect, which was the first that was proposed in that original paper of Berlin. So the idea of the orbital Hall effect is very similar to the spin Hall effect. You apply an electric field, so you have a current crossing the material, and it generates a transverse orbital current. Now, the main difference, thinking about and most of the first calculations on that were related to the intrinsic orbital Hall effect. And in the next year, now there are maybe a few, 3 to 4 works discussing also how we can do that with extrinsic mechanisms. Well, what's the main difference between the spin Hall effect and the orbital Hall effect? You don't need spin orbit coupling for the orbital Hall effect. The spin orbit coupling can be 0. In fact, what plays the role of the spin orbit coupling here is the crystal field and the hybridizations that you have between orbitals that come from breaking symmetries, for example. Well, as in spintronics, you need to inject currents, and you can do that through orbital effect, but you also need to detect it, right? And the main issue with the experiments is exactly because how you differentiate spin accumulation from an orbital accumulation. At the end of the day, you are measuring magnetic moments. They are the same, right? So how do you know you're detecting one or the other? And the main strategy so far in metals has been to use very light metals with very weak spin-orbit coupling. So if anything is detected, we can rule out the effect of spin-orbit coupling. And this is what was done in the first direct experiment showing using MOOC, where they show they have a current, they generate the orbital Hall effect, and in this surface they look at with MOOC at the magnetization at the surface, and because they're using titanium, which has a spin orbit coupling of orders of magnitude smaller than platinum, when they look at the accumulation, it's maybe an order of magnitude smaller only, and they know they are looking at orbital Hall effect. And this experiment was also repeated with chromium in a group of Kawakami, and with the same technique, and they got similar results. Well, the same way we have the Rasch-Bodenstein effect for spins, we also have the orbital Rasch-Bodenstein effect that was proposed long ago. But the question is how we can measure this effect. And the way, but recently there is a work from French group where they actually managed to measure the inverse orbital Rasch-Bodenstein effect. And this is done the following way. They pump both orbital and spin into a 2D electron gas that has orbital textures. So we should expect orbital Rasch-Bodenstein effect. And they measure the inverse effect, that's the generation of a current because of an orbital accumulation. So an orbital accumulation should generate a current to the inverse orbital Rasch-Bodenstein effect. And they do this and they apply voltage and they measure voltage in different orientations, and they manage to measure the AC current, and they look at the symmetry of this current in space, and the symmetry it's only associated to the orbital texture, not the spin texture. So they characterize this as the orbital, the inverse orbital Rasch-Bodenstein effect. The same way, there are many magnetoresistances with orbital origin. There are also magnetoresistances with, there are many magnetoresistances with spin origin, like the Henle magnetoresistance. There are few works measuring the equivalent magnetoresistance for orbital characters. They also use, for example, the group of Pietro Gambarella use manganese and compare the results for the magnetoresistance with platinum or tantalum with very strong spin-orbit coupling. They see the same magnitude of magnetoresistance, so it's a Henle effect that's associated now with an orbital origin. Just this is, I don't want to spend too much time on this. Well, there is also the same way there is spin transfer torque. I don't know if you're familiar with this, but the idea of the spin transfer torque is that if you introduce a spin current or you have a spin accumulation at the interface with the magnet, this can produce a non-equilibrium spin accumulation in the interface of a magnet. It can produce a torque in the magnetization of the ferromagnet, right? And it can even switch this magnetization. This is what we know as the spin transfer torque. Well, there is something similar, but with the orbital currents or orbital accumulations. And the idea is the same. You apply an electric field, you have a current entering the material that produces orbital Hall effect, for example. It will produce either an orbital accumulation at the interface or an orbital current, and it enters the material and can switch the magnetization. The only difference is that, different from what happens in the spin transfer torque, this is a two-step process, because the non-equilibrium L enters the material, but it has to be transformed in a spin accumulation to the spin-orbit coupling in the ferromagnet, and this spin accumulation that interacts with this the magnetic moment to exchange and can produce the torque. So the ferromagnetic material needs to have spin-orbit coupling. Otherwise, this orbital current does nothing in the ferromagnet. Okay. Just this year, there appear a few works doing the inverse effect of the orbital torque, which is the orbital pumping. So in the case, thinking about spins, in the case of the spin transfer torque, we have, and thinking about the spin-Hall effect, we apply a current in a material with spin-orbit coupling. It generates a transverse spin current, and this spin current enters the magnetic material and processes the magnetization. In the spin pumping, we have a magnet that's oscillating, for example, through ferromagnetic resonance. It injects a spin current, and because of the inverse spin-Hall effect, it will generate a transverse charged current that can be detected. So it's a way to detect the spin pumping. So, well, this exactly the same thing can be done with orbital systems, and the difference is that this material doesn't need to have any. It can be a light metal, and you still can see these effects. Another nice experiment, and this it's even a nice experiment in spintronics, is the use of spintronics to generate terahertz pulses in a very large range of frequencies. So this has been done for a while, and now actually for those working in optics in the terahertz limit, this is a very nice way to actually have terahertz spectrum in a large range. And the idea is the following. You have a laser pulse in the picoseconds. It hits a metallic system, in this case, a ferromagnet that's in contact with a non-magnetic material with spin-orbit coupling. And because and then it changes the group velocity, everything in this ferromagnet, because it's hidden. And because these materials, they have different properties, there is a net current flowing in this direction, and it's strongly spin polarized. Right? When it enters the material with spin-orbit coupling, spin up and spin down are deflected in different directions, and because there is only one population, you actually generate a charge current, which is transverse to the spin current. And it decays and emits a terahertz pulse. So this is a very nice way of producing terahertz pulses. And there are, this is now in the market. And the same group that was doing this began to do the same type of experiment, but now using a non-magnetic material that doesn't have any spin-orbit coupling. And they actually can see exactly the same thing. Now, the difference is that if the ferromagnet doesn't have any spin-orbit coupling, you don't see any emission. You don't see the emission because you're not injecting orbital currents in this material. So you need to have spin-orbit coupling in the ferromagnet so that the spin polarization also translates it in an orbital polarization that enters the non-magnetic material and then produces the inverse orbital Rashburn-Stein effect and emits light. So this is an overview of the recent experiments in this field. This is just the last 2 years, as we saw. And now the question, because up to now I'm talking only about metals. So is there any life beyond metals in orbitronics?
I've got just a question before we move on. It seems like you're just taking a spin and you're applying to orbitronics. Why is this happening now and not 10 years ago?
Well, how things are happening in physics. Yeah. I can give my take on this. So Wernicke, Vick, Hughes, and Deng, they wrote this paper about orbitronics, the name Orbitronics and everything. But they were beginning to see topological insulators. A few months later, topological insulators appeared. Everything was moved to topological insulators, and nobody cared about this. It's just about physics, how it works. And they never came back to look at this problem again. And actually, if you go to this paper, there are similarities between what they were doing there, and then when you put in some of these systems the spin orbit coupling, but then only discussing with them to know what they had in mind when they wrote this paper. But my impression is that things were going in one direction, this disappeared, and then suddenly topological insulators, all the physics there, spin orbit coupling, and so who cares about this, right? This is more complicated, right? Okay, so, but now we are beginning to see, so just this year, beginning to see some works on quantum materials. So in this case, for example, is an experiment where they use orbital torques to manipulate the magnetism of this antiferromagnetic line semi-metal, and they can actually switch the magnetization of the magnetic state of these antiferromagnets, and the critical current that's used to do this switching is much smaller than the one if you use only spins. Okay, and this is because the generation of these orbital currents is more efficient than spin ones. This is what they claim with it. Also, there is another paper using ARPES to show that in a chiral topological semi-metal, if you look at the white nodes in K space, around them, you have actually orbital angular momentum monopoles. And these monopoles are interesting because if you think a system with these monopoles, you can have the orbital Rashba-Ildenstein effect, where the orbital magnetization points parallel to the charge current instead of perpendicular. So these are a few things that are beginning to be seen in quantum materials. And now I will move to orbitronics in 2D materials and discuss, why 2D materials are interesting. And some of the ideas are valid also for other quantum materials. But because you normally hear about 2D materials is that, it's very easy to tweak their properties by gating, stacking them, changing the angle between them, doing like twisted materials, applying strain. They are very flexible. But what is interesting for in 2D materials, when you think about orbitronics, is that the constraint, the dimensionality constraint of 2D materials actually puts a strong symmetry constraint in the z direction with very characteristic crystal fields, which actually work as some kind of orbital filtering because they remove some degeneracies that we have in the orbital character of the system, right? So it can throw in and out some orbital hybridizations, and this is interesting for orbitronics. And you can actually do that by changing substrates as well. So, and an example of this is bismuthine. Depending on the substrate, you can actually shuffle PZ orbitals that were at the Fermi energy down to very low energies and promote, for example, a quantum spin Hall insulator. So we can do some orbital filtering. Also, low dimensionality to the dimension means that we have orbital textures. This is known since the 2D electron gases from oxides. And orbital textures are important for orbital Rashba-Ildenstein effect and even for orbital Hall effect. And also many of these 2D materials have electric polarization or are even ferroelectric, and this plays also a way of manipulating the orbital angular momentum by electric fields. So now I'll begin with our works and our results, and I will use transition metal decoupled ions to exemplify part of the physics that appears when we explore the orbital Hall effect, particularly in several 2D materials. So I use this as an example, but many of these things can be generalized to other systems. So TMDs, they have, so I will focus on two structures of TMDs, the 1T and the 2H. So they have a honeycomb lattice structure where we have chalcogenes, a pair of chalcogenes in one sublattice and transition metal in the other sublattice. In the case of 2H TMDs, the chalcogenes are on top of each other. So we have a mirror symmetry Z, but you have broken inversion symmetry. And conversely, in 1T, you don't have this inversion, the mirror symmetry, but we do have inversion symmetry in Z. Well, first, the case of the 2H, where you have broken inversion symmetry, what you have is that because of the broken inversion symmetry, you have Wally physics associated, and you can have Wally Hall effect. This is an illustration of the Brillouin zoom of a material like that. You have K and K prime. And if you look, because of the spin orbit coupling, if you look at the top of the valence band, it's spin polarized depending, and the sign of the polarization depends on what value you are looking, which means that you have an effect at the spin value locking and in TMDs. And this can be used in spintronics and optospintronics, but they don't have spin Hall effect in the vicinity of the band gap. So let's begin with a very simplified T-bands model for TMDs that work quite well close to the band gap. And this is the LZ operator in this basis here. We can calculate the energy spectrum with and without spin orbit coupling. And if we look at the valence band, doesn't matter if they are split or not, and you look at the expectation value of L, this is the orbital texture, we can see that depending on the value, the orbital polarization is the opposite. The orbital texture is in the opposite direction by these columns, right? Which means, and it happens even without spin orbit coupling, which means that there is an orbital value locking that precedes the existence of the spin value locking, and even explains it, right? And the energy scale of this, it's only related with the orbital dependent hoppings in the system, so it's the order of a few electron volts compared to the milli-electron volts of the spin orbit. Now, if you look at the, in red is the spin Hall conductivity, we can see that inside the gap, if close to the gap is almost zero. We can also calculate the orbital Hall conductivity. And surprising enough, there is a plateau that appears in the orbital Hall effect, and regardless of the existence or not of the spin orbit. So a first question that emerged is, okay, in this system we have Wally Hall effect, so maybe what we are seeing here is a Wally Hall effect, and because of the Wally orbital locking, we are just witnessing the Wally Hall effect. So to clarify this, we try to look at a system with inversion symmetry that has zero Wally Hall effect. So we look at the bilayer MOS2, and now we are using Benich calculations and Paul flow to calculate the transfer properties. And again, we see the plateau for the monolayer. When we look at the bilayer, we see the same plateau, but twice as high. So it not only survives to having the inversion symmetry, but seems something with a topological origin. Now, the question that appears, well, this is not a topological insulator. So how come we have this plateau? And if we have this plateau, who is carrying this orbital angular momentum inside the gap? Because this is not a TI, doesn't have at states, right? But funny enough, these materials do have at states. So 2A TMDs were known for having these at states crossing the gap with not much explanation. They were always tricky. And we actually, but different from a TI, like a BHC model, they have twice the number of crossings that you should expect in a TI, right? So this is the characteristic of the crossings. Now we looked also at 1T TMDs. They also have the plateaus we saw. And we actually saw they also have edge states crossing the band. So, and they appear only in some orientation. So they have metallic edge states, like zigzag edges. And these edge states can carry the orbital angular momentum. Now, to discuss the origin of these edge states that were puzzling for a while, we need to discuss a little bit high order topological insulators. So I think here we have a lot of people familiar with high order topological insulators. So in TIs, we have the normal TIs, we have global symmetries like time reversal symmetry that protect the topological edge states. However, we can have crystalline topological insulators where the protection comes from crystalline symmetries, right? The symmetries of the crystal. The problem is in systems like that, when you go to the boundary, you can have a lower symmetry than compared to the bulk. So you end up having gapped edge states. So a high order topological insulator is basically a crystalline topological insulator where in D minus one dimension, the boundary states are gapped, but in D minus n dimensions, you can have boundary states. So in the case of a 2D Hottie, we have the edge states are gapped, but you can have corner states inside the gap. There are several classifications for this, depending on the symmetry, because there are many symmetries that can protect these states. But one characteristic that appears in most of these high-order topological insulators in 2D is that they have a finite polarization in the unit cell, a multipolar. Oops, sorry. So what was lost for a while is that 2H TMDs are hotties, and there are some work discussing this, showing that even if you cut a TMD in armchair sides in a triangle, you actually end up having these corner states. And we also calculated classified 1T TMDs, they are hotties as well. Now, the funny thing about these hotties is that if you, instead of cutting, like I cut this triangle, we cut, so, and then because you have this charge at these corners, you have a net polarization, right? Now, if I cut my system in a way with edges that are perpendicular to this polarization vector, you can think that this localized charge, they spread in the edges and they form in-gap edge states that can cross this gap. So we can actually predict materials that have in-gap edge states that can carry orbital currents, which are the 2D hotties. And actually, we tried with high throughput calculations, and all hotties we saw, they do have orbital Hall effect plateaus. Now, let's explore a little bit more the role of these edge states. So we can go back to that T-bands model. With the T-bands model, we can still you have the TMD, but we can modify the hoppings, and also with the same model obtain a normal topological insulator. Now we have, we use Landau-Buttinger calculations to QuMat, and we have two different types of devices. One that only have metallic edges, and the other one that has like cut. So we have two types of edges here. In the one that we only have metallic edges, we can see that in green here is the orbital Hall conductivity. It's a very small system. This is why it's very noisy. We do have orbital Hall conductivity inside the gap. If we put it in the other direction, we see that there is no orbital hole conductivity inside the gap, which is different from what happens in the TI, that, of course, regardless to the way you cut a system, you always have spin and actually orbital currents inside the gap. Now we can also look at the effect of disorder in a system like that. Now we move to a bigger system and look in the energy region inside the gap. And again, comparing TMD and TI, we see here we have the orbital hole conductivity in the TMD. It survives inside the gap, it survives to disorder, but we can see it's not immune to disorder, right? It's modified by disorder. And funny is that even in a TI, although the spin hole conductivity is protected, the orbital hole conductivity is not protected. So you see, of course, it's more robust than this one, but there is a decrease of the orbital hole conductivity when you increase disorder, and there is no change in the spin hole conductivity. So it's not topological in the same way of the spin hole conductivity as we should expect. Well, I was talking about disorder, so we need to look at disorder with a little bit more details. And one important aspect is that it was proven many years ago that in some systems, depending on the symmetry, if you calculate the effect of disorder, you can actually cancel out the spin hole conductivity. So it's, for example, in normal 2D electron gases, like in semiconductor 2D electron gases, if you calculate the intrinsic contribution of the hole conductivity is finite, but then if you include the extrinsic one cancels the other, and then there is no spin hole conductivity. In other materials, like depending on the symmetry, you can have a huge enhancement of the spin hole conductivity because of disorder. So it's important to check this out. And there are three recent works discussing the effect of impurities, and the results are all in opposite directions. So there is a paper from Dimi Kusser on using quantum kinetic equations with Gaussian disorder, and then they show, and maybe because of the type of approach they are using with the Gaussian disorder, that the orbital Hall effect it's decreased by extrinsic mechanism, but this is independent on the concentration and the strength of disorder, which is a little bit strange. There is also Boltzmann transport calculations in a simplified PX-PY model, showing that depending on the symmetry, the orbital Hall effect can be, the extrinsic contribution can cancel the intrinsic contribution, but in that scenario, also the orbital Hall effect does not depend on impurity and the strength. And now numerical calculations in real space, where the orbital Hall effect depends on this orbital strength, can increase and then decrease. So together with the group of Iris Ferreira from York University, we've been looking at this problem using a self-consistent diagrammatic theory that we sum over all the events of one kind. So it's a non-perturbative approach. And we look at short-range impurities. So it's not like Gaussian impurities as before. And the scenario we see is different from the other ones. We do see an increase of the orbital Hall effect because of disorder. And it can even change signs. So this is the original, in green is the original orbital Hall effect, only the intrinsic contribution. And then in blue and red, the total orbital Hall effect with different strengths of disorder. So we can see an increase of this orbital Hall effect that goes with the inverse of the empirical concentration and the strength. And this is a characteristic of skew scattering mechanism. So we see skew scattering regime that's producing this extrinsic orbital Hall effect. And we can actually build a diagram of the impurity concentration and the Fermi energy. and that separates a region of parameters where the extrinsic contribution is larger than the intrinsic one, and the other one when the intrinsic contribution actually dominates. So we have the two regions. Now, we are now in collaboration with another colleague from Brazil, Anderson Barbosa. We are looking at, again, mesoscopic devices, like the one I was showing before, but in a different model. We have a very simple model. We didn't want to have a high order topological insulator or nothing like that. It's just a SPXPY model in a square lattice. This is the first model that was used by Don Wuko and collaborators to discuss the orbital Hall effect. And this paper is quite important in the field. This paper was fundamental to the increase of the activity in this field and the discussion of the relation between orbital textures and the orbital Hall effect. So they use this model. This model is very much used in the orbitronics community. And if you throw in a hybridization between S and P orbitals, you can have orbital Hall effect. If you don't have this hybridization, the orbital Hall effect is zero. This is more or less what we have. And what we are doing is that we have this Hamiltonian, and now we include on-site disorder. And this is the device we're looking at. So we have, we inject current from in this, we have inject current in this direction, and this system goes on to L0. So we are generating orbital Hall effect in that region. But we can have a much larger region where the spin current can, you can have relaxation processes in this region where we are not having the generation of the orbital current. So we can measure the orbital Hall effect, calculate the orbital Hall effect, but also the relaxation processes. So first focusing on the orbital Hall effect, so L0 is equal to L. We look at the effect of, if you change the maximum value of the Anderson disorder in electron volts here, or in units of E actually. What we have is that depending on this hybridization, on this hopping between S and P, we can have different orbital Hall effect. Can be positive or negative, stronger or weak. So for example, for T equals 0.5 that we use very often, we have a positive orbital Hall effect. Now we include this order, you can move to negative orbital Hall effect, and this effect is increased very much, right? And then it begins to decrease. If you look at the, sorry. Okay. So the contrast, we can, I think you can't really see my, I have a highlight in this region, but it does not appear. So what we have here is a region where we do have a diffusive regime, like in the previous slide. And in the diffusive regime, in these dashed lines, we can fit the orbital conductivity being proportional to the inverse of the strength of the disorder. So we have something that seems like skew scattering regime as well. We can also look now, looking at this device again, but now we can increase the value of L, so we can have relaxation processes, and we can look how this current is detected here when you change the orbital current is detected here when you change L. And we see that depending on this, there is always a decrease of this current with L. We can plot this in log scale, and we can see for 0.5, it's difficult to see if you can have an exponential fit, but for the other three U's, we can have an exponential fit. So this is an exponential decay, and we can have the relaxation length for this type of device. And for example, for this green curve, it's about 200 lattice constants. It's quite long. Now, if you calculate, we can also calculate the orbital Hall angle, which is the ratio between the orbital Hall conductivity and the charge conductivity. And we can see that it's almost constant. Although there is a decrease in the orbital Hall conductivity, there is the same decrease in the charge conductivity when you change L, which my interpretation is that tau, the relaxation time of LZ goes with the relaxation time of the charge, which means, well, and this scenario is different from some other calculations on orbital relaxation times in a different system. So we are now trying, so these are the first works trying to extract relaxation processes, relaxation times and lengths in orbitronics. So there's a huge interest. Well, with this I come to an end. I would like to thank my main collaborators on this, Roberto Bechara and Márcio Costa, professors at Fluminense Federal University. Tarek Cisne is a former student and postdoc who just got a position at the same university. Luis Canônico is a former student who is now at ICM2 in Barcelona, and some other collaborators that have collaborated here and there. I would like to give some very general remarks. First is that orbital angular momentum manipulation in solids, it's finally a reality. So I expect that I convinced you with the experiment that we can actually do that. We can use light methods for many effects that we normally had to rely on very heavy elements with strong spin-orbit coupling. It's still quite difficult to separate spin and orbital angular momentum dynamics, but I think the main idea is that you can couple the two and extract the most of both of them. Up to now, we still have a very superficial understanding of the orbital phenomena. So if you ask me how to maximize the effect, I can give you some ideas, but we don't have a systematic analysis on this. So there is plenty to do, especially if you think about orbital filters, like you have spin filters, orbital torque, which is 100% orbital. It doesn't need to go through transforming things into spin and then switching magnetization, and a better understanding of the orbital magnetism actually to do these other things. In terms of the 2D materials, we see that we can have very large orbital Hall effect without spin-orbit coupling. We have skew scattering mechanism that can strongly enhance the orbital Hall effect in 2D materials. Our group is responsible for finding these orbital Hall insulators that present sizable orbital Hall plateaus, and it's connected to high orbital topological insulators. But there is a lot to explore in connection with the geometry and topology in 2D materials and understand the connection with orbital physics. Also, Rashba orbital Elgenstein effect should be quite important in low symmetric 2D materials, and we still have a lot to see in terms of the mechanisms for the orbital Hall effect, as I was discussing in the previous slide, and also orbital relaxation that's just started. Well, we've done many works on this. I leave some references here. I talked just a little bit about my works. Thank you very much for everything. Thank you very much.
When you first showed the edge states for the EMBs, you showed this conductivity plateau in the gap. It seemed to me like this conductivity plateau was slightly above 3, so not an integer value, but slightly above it. Is there a specific reason why it's not integer values?
Well, first, we don't know exactly. It doesn't have. I can actually I calculated that channel number for the orbital angular momentum operator, like you do with spins. But in principle, there is nothing that says should be quantized. But you know that the plateau. Let me go back to a plateau. So Even for the quantum spin Hall effect, there is a misleading understanding that the quantum spin Hall plateau should be quantized, which is not correct. It's only quantized if the spin is a good quantum number,
Yes.
but it's not normally the case. If you have Rashba, for example, you can have a quantized a plateau. You have a plateau like this, but the value is not quantized.
Oh.
So it's still a topological insulator. It only if you close the gap and open it again, it's not a topological insulator anymore because it's it's topological. But the plateau is not quantized. It's only quantized if the spin is a good quantum number. LZ is not a good quantum number in the whole system, right? It's actually good in the K and K prime. LZ, only at that point it's a good quantum number. Everybody, every else in K space is not.
So if I look at the Terrace emission, you use this for Terrace emission from people you discussed.
Oh.
It's like the signal noise levels. It looks like rather weak compared to spintronic emitter.
What?
If I look at then the signal you are presenting from that paper, it looks like the efficiency of conversion compared to spintronic emitter probably a little bit on the weak side.
Yeah.
Is this intrinsic or
What?
Is this an intrinsic effect or is this?
Well, there is nothing. No, it's not. Well, it's nothing. First, it's very surprising there is an effect, right?
Sure.
Now, no, the thing is that this field is at the beginning.
Yeah.
So the question is how you actually maximize, optimize this.
Yes.
So this is a proof of principle.
Yeah.
Okay, we do have this. It depends on and you can see that it depends on the fact that you have nickel, for example, that has spin orbit coupling compared to having a ferromagnet without spin orbit coupling. So then you have different intensities of the response and things like that. But to maximize this, you have to play with the material that generates the orbital Hall effect. And we have very little understanding of how to maximize this.
In terms of the disorder, you showed the conductivity in terms of disorder, right? And
yeah.
Is this quantized in terms of disorder, or is it something?
No, it's quantized. No, that this.
No, in the next one you showed that is in terms of disorder, right?
Mm-hmm.
Is this quantized in terms of the disorder, or
no? It's not quantized. Well, I'm showing some points because the simulation, and so for each point you have a realization, many realizations, but it's not quantized. From what I get, this you have actually more than two regimes. This is a regime where you have diffusive regime. This is probably at the beginning it's ballistic, right? It should be ballistic, and then you move to a diffusive regime, and then you enter in something that's more localized, but it's in the continuum.
We have one. Can one play with bands to imprint the angular momentum
In playing with
in higher bands?
Yeah, I think, well, these are, so you can have, in some sense, you can have situations where you have you can play with inverting bands, even without, so that's the thing, even without spin orbit coupling, you in principle can invert bands. Actually, this is what you see in this. I told you you can have the same model. And for a TMD, TI, the same, you begin with a model with 3 orbitals, and you can have TIs, TMDs, or just systems that a high order topological insulator or system that doesn't have anything. But to have strong orbital Hall conductivity, sometimes you invert bands, even without spin orbit coupling, just invert because of some symmetry breaking that you include in the system, and because of this inversion, you change the orbital character at the Fermi level, and then you see
Because I'm thinking more like manipulating, like making lattices where you manipulate on site what kind of orbital.
Yeah.
For instance, they did with cold atoms, these 2D lattices, which is a checkerboard with S, PX, PY, S, PX, PY. So a checkerboard between S and PX, PY. And then in the presence of interactions, you can see that you generate PX plus IPY and you get on-site orbital currents.
Yes, and then you
that come from the orbital manipulation.
Yeah, for sure. This is what I was calling somehow the orbital filtering. Yeah, if you can do this in an artificial lattice, the problem is maybe the only problem is how you measure the anonically whatever there that you show that you have orbital current, let's say.
Yeah.
But maybe for orbital or orbital magnetization. But yeah, it might be interesting to do something.
I could show you some of the experiments that are done. Okay, yes, please, Minho.
I'd like to give the word to Marcos.
Oh, yes, please.
Can you hear me?
Yes, we can.
Okay. Was a nice talk, Tatiana. Thanks for it. I have a question, maybe more from an experimental point of view, because you mentioned that a lot of the experimental work has been done using light materials, right? Light metals, because then you can get rid of the spin-orbit coupling. But is there a way that we can actually measure just or get kind of an experimental evidence of orbital accumulation without having to rely on the lack of a spin-orbit coupling? Can we separate spin and orbital contribution without just removing spin-orbit coupling?
Well, in some situations, one thing is the sign of the spin-orbit coupling, right? Because you can have, so actually what I didn't discuss here is that the first experiments actually done in this, they were, and even in this experiment, they discussed this a bit, you can also check the sign of the spin-orbit coupling, that depending on the material, you should have a sign inversion. And then when you look at the accumulation, you can have, like, in some situations, that you sum up the effect of one magnetic moment and the other one you subtract, depending on the sign of the spin-orbit coupling. So you can also play with the sign of the spin-orbit coupling. But a measurement that separates the two, I think it's more difficult, right? Then, because in many situations you don't have, in some situations we might have different symmetries. But in general, you know that if you think about transport measurements, the symmetries that you have for one, you're going to have for the other. So, but playing a little bit with the sign of the spin-orbit coupling. So materials that are similar, but with the inverse sign of the spin-orbit coupling can give you hints on this, for example. I think that's a way to look at it. I don't know if it answers you.
Maybe I can just add
the coupling in the ferromagnet as well, right? Because if you have a big change in what happens in a ferromagnet, because it has spin-orbit coupling or not, there is also an indication. Sorry.
Okay, thanks.
Any other question online? No? Okay. Then let's thank Tatiana very much.